All right, guys, quiet down so we can do this, please.
Your face.
All right, so potential energy curves. All right, so this is a thing that I don't know that I honestly ever saw until last year when I taught this class. And it's pretty easy. Okay? So, potential energy curves. So, do you guys agree that, like, if you look at the gravitational potential energy, the gravitational potential energy of a thing depends on the height and the mass, right? But so for a given object, the mass is fixed. So we can very easily make a graph of the gravitational potential energy of this pen as a function of height, right? Different heights would give us different gravitational potential energies, right? Similarly, for a spring, we could make a graph that told us how much elastic potential energy the spring had as a function of how far it was stretched, right? Okay? So that's kind of the gist behind this, all right? So, do you guys have this in your notes?
Yes.
Okay, cool. I couldn't remember if I'd run out copies. All right, so here's just kind of a list of the things that you ought to be able to do, by the end of this lecture here. It seems like a lot, but it's not that much. So anyway, I'll let you read through those at your own leisure. Go back at the end and make sure we got them all. All right, so this first slide here is basically just for review. So remember that we can write the force exerted by a force as the derivative of the potential energy associated with that force. Don't forget about that negative sign, right? Okay? I really need to rewrite these notes. Okay, so anyway, so there is a connection between the potential energy associated with the force and how much force is being exerted. All right? Now, keep in mind, what I usually talk about is, when I usually talk about TE, most textbooks just call E mech as in mechanical. Okay? So we can express the total energy or the mechanical energy of a thing as the sum of the potential energy and the kinetic energy. Okay? And so you could certainly rewrite your kinetic energy as just being, whatever your total is minus however much potential energy you've got. Okay? So, nothing too mind-blowing there. All right? You know what? Sorry, I'm just thinking about the best way to go about this. Sorry, give me 1 minute. I'm processing here. Yeah. Okay. You know what? Let me do this. I'm going to jump ahead in the notes. I think this will make our lives easier. There's a slide that looks like this, so jump ahead to that one for me real quick. Yeah, sorry. Okay, so do you guys agree we could make a graph? This would be a potential energy curve. I guess our position would just be height, right?
Yep.
So usually the horizontal axis would be position, okay? But in the case of GPE, that position is vertical height, so I'm just going to call it H, okay? And then on our vertical axis, we've got GPE, right? So what would that graph look like, you guys? I see some of you guys. Okay. Yeah, wouldn't it just do this? Wouldn't it just be a straight line, right?
Yeah.
Right, because GPE is just mg times h, right? So this would be a slope, or a line with a slope of mg, right? Cool? And notice, what's the derivative of this? Well, so here, so the slope is mg, right? Okay, wouldn't the force of gravity be negative mg? Right? So this is sort of illustrating the fact that if I take the derivative of this curve with respect to my position, it gives you negative force, right?
Yes.
Right? Because the force of gravity would be negative mg, because gravity pulls down, right? Make sense?
Could you put that?
All right. Follow? All right. We'll come back to this equilibrium point thing in a minute. So that's a potential energy curve. Questions of it? Okay. So let's do one for elastic potential energy. Notice with a spring, your x can be either positive or negative, right? Depending on whether you stretch, or squish it. Okay, well remember, EP is just 1/2 k times x squared, right? So it's just a parabola, right?
Yep.
So, cool? It's the worst parabola ever drawn by a human being.
This mechanic can do worse.
All right.
Or not even worse.
All right, so are we all good with this? All right, so notice that if we take the derivative of this, sorry, I'm waffling between my PE and U. I keep switching back and forth, and that's probably, is that frustrating anybody? Yeah, a little bit. All right. So that would be the derivative of this, right? And that gives us what? Let's see, kx, right? Oh, but that's equal to the opposite of the force exerted by a spring, right? Because the force of a spring is negative kx, right?
Yep.
Okay, and that sort of makes sense too, right? Over here, my slope is positive, would indicate a positive force, right? But if you stretch a spring in a positive direction, isn't the force negative?
Yep.
Right? And over here, if I stretch a spring in a negative direction, then the force would be positive, right? Follow? Okay, so those are potential energy curves. Questions on sort of what they mean? Okay, so we could certainly come up with other conservative forces for which we could associate a form of potential energy. And so we could get any different assortment of potential energy curves. All right, so let me rewind back again to this slide. So I was here when I jumped ship. So look at that slide right there. Back a page or two. All right, so what this red graph here represents is just some theoretical potential energy curve. All right, it's obviously not for gravitational potential energy. It's obviously not for a spring. It's just for some thing, okay? And there's our potential energy curve, all right? So, equilibrium points. So an equilibrium point is a point where your net force is 0. So it's the maxes and mins, right? Because remember, you're at an equilibrium, the slope of your potential curve is the opposite of the force, right? So we want to find the spots where your slope is 0, where your net force is 0. Okay? So it turns out there are 3 different types of equilibrium points. Okay? That are what are called stable equilibrium points, unstable equilibrium points, and neutral equilibrium points. Okay? And the definitions of them are described on the previous slide. Okay? So, here they are right here. So, a particle in what's called neutral equilibrium all right, in order for it to be a neutral equilibrium, it needs to be stationary. I do not like this definition. It's got to have only potential energy, which obviously, if it's stationary, that means it doesn't have kinetic energy, so it would only be potential, right? It's got to have a net force of 0. Here's the actual, sort of the meat of the definition. If it's displaced to one side slightly, it would remain in its new position. All right? An example would be a marble on a flat table. Okay. Wow, that is really worded badly, isn't it? I'll tell you what. Let me do this, and then I'll come back to the definitions. So what do we got? Red is neutral. Blue is unstable. All right. So, do you guys agree the slope here is 0? And the slope here is 0? Those are neutral equilibrium points. All right. They're neutral equilibrium points because if I have a particle that's here, notice, so I'm saying it's at, this position. All right. If I move it to the left or the right a little bit, well, then it's going to just stay there, right? Because my net force is still 0, right? So there's nothing sort of trying to change its positioning. Okay? So those are neutral equilibrium points.
So there's like room for it to move?
Yeah, kind of. Let me explain the other two, and I think this will make more sense. I shouldn't have started with neutral. All right, unstable equilibrium. All right, imagine I had a point right here. I had a thing right there. Okay, so at that point, it's got a potential energy of 3 joules, right? Okay, and think about the forces on it on either side of it, right? If you move to the left, if you move it this way, you've got,
I'm just wondering, is there like any real life objects that we could like
equate this to?
Yeah.
An object like a roller coaster, literally.
Oh, okay.
You know what I mean? Where you write the potential energy of the car as a function of the position along the track.
Okay, so the track is literally.
Yeah, the track is literally this, yeah. Okay, man, I am struggling today, you guys. I'm sorry.
It is Monday.
Man, I know, but like extra Monday E. I feel like I'm more off than usual. Okay, why can't I say what I want to say here? So if you suppose we have an object that's got a position so that it's at x3. All right, that's going to be unstable equilibrium. All right, let me give you the sort of intuitive definition for why it's unstable. The idea is, so if you've got an object that's at a position of x3 and you give it a teeny little push either to the left or the right, you okay, Seba?
Yep.
Okay. Oh, I got you. Got an appointment. Okay, so if you push it a little bit to the left or the right, what's going to happen is the conservative force associated with this potential energy is going to move it farther away from that point. Okay? So if I push it a little bit to the right, whatever that conservative force is going to pull it even farther to the right. Okay? Exactly like a ball balanced at the top of a hill. If you push it a little bit, it's going to roll down the hill, right? Same thing. If you push it the other way, it's going to go that way, right? Does that make a little bit of sense? Yeah, Teddy?
Does this assume the force being applied is conservative?
Yes. Oh, you mean to displace it, you mean?
Or the force that's to the right, in terms of the potential energy, that force.
So, yes. Yes. Because otherwise you wouldn't be able to talk about the potential energy. Okay. So that's an unstable equilibrium point. So why is it unstable? We should probably analyze a little bit more. So let's see. So if it's here, if I push it this way, so let's see. At that point, my slope is positive, right? So that means that the slope of that is positive, right? Which means the force on it is negative, right? In other words, the force is pushing it even further into a negative direction, right? Does that make sense?
So maximums are always unstable.
Exactly. So maximums are always unstable equilibrium. Yep. All right, and similarly, if you go the other way, your force is going to be positive, so the force is going to push it farther away from that equilibrium point. Cool?
Would a maximum, so like if, I'm sorry, if it was going and it bottomed out at the top again, wouldn't that still be a maximum, but also be a,
Say that again.
like, okay.
A local maximum, I guess. Is what
Oh, okay, okay.
Okay, good. Yeah. Yeah, you're right, because this is a max, but not a local max. Yes.
So right at the point x5, is that also unstable?
Say that again, right at the point x5.
Yeah.
Oh, shoot, there is a term for that. I see what you're saying, because it's going one way, it's neutral. Ooh, shoot. I'll have to look that up. That's my bad. I don't remember what that is. That's called. Okay. All right, and then finally, these guys here are stable equilibrium, right? And again, it's the exact same idea, that if you displace it, if you push it to the left or right a little bit, the conservative force responsible for that potential energy is going to want to bring it back to where it was. Okay? So Zach's question was a great one, and I think an important one, which is this. So what is this? Like, give me an example of a thing that has this potential energy curve. And the easiest example is a roller coaster. Right? So if you imagine this as a roller coaster. All right, well, while you're in the station, here's your potential energy, right? Then you go down that first, so you've got a roller coaster where the station's up on top of the hill. Right? So, you know, and then you roll down the hill and up and right? But your potential energy is going to be proportional to your height, right? Does that make a little bit of sense? Okay. So, real quick over here, I got this force graph. Where did that come from? It's the negative of the derivative. Cool. All right. Now, so the way that most of these problems are going to be set up is as follows. They'll give you a potential energy curve, and then they'll give you how much mechanical energy you got. Okay? So, why did that happen? All right. So let's suppose we had a thing, you know, a car on this roller coaster, we'll say, and it only had 1 joule of mechanical energy. Okay, think about what that roller coaster would be doing. Could the roller coaster ever get up to here? No, because if the mechanical energy is only 1 joule, that means that the sum of my potential energy and my kinetic energy is always 1 joule, right? So when the car is here, what's that telling you? What's the potential energy right there, you guys? 1 joule, right? The conservative force is going to pull it this way until it gets to right here. Now what's going on? The kinetic energy is 1 joule and your potential energy is 0, right? Okay? The conservative force is going to take that kinetic energy and convert it back to potential energy until you get to here. So this car is just going to go back and forth in that little well there. In a frictionless roller coaster. Yes? Follow? All right. Now, what if the mechanical energy was, oops, man. I had a tough time getting out of bed today. Maybe I shouldn't have. All right. What if we had 3.5 joules of mechanical energy? What would this thing do?
Go up the second hill.
It would just cycling back and forth, right? Does that make sense, you guys? So the mechanical energy line sort of represents your oscillation is going to always occur below that line, right?
Yeah.
Okay? Now, if your mechanical energy is, say, 2 joules, then there's 2 possibilities. You're either going to cycle in this well, or you're going to cycle in this well, right? Does that make sense, you guys? All right. What if your mechanical energy was 5 joules? What would happen? Yeah, it looks to me, if your mechanical energy is 5 joules, then depending on which way it's going, so suppose the thing has an initial position of x2. So suppose it starts right here. Okay? If it's moving to the left, then what's going to happen is it's going to move to the left, it's going to go up to here until it hits this point, go back down, and just keep going that way, right? Cool? All right. Now, So these points where your potential energy equals your mechanical energy, your total energy, are called turning points. Why would that be true, you guys? Well, that's where you turn around, right? Because if you think about this thing starting here, if I push it this, or if it's moving this way with a mechanical energy of 5 joules, as it moves that way, it's going to lose lose kinetic energy and gain potential energy. When it gets to this point, what's the kinetic energy going to be? 0, right? And so then the conservative force pulls it back the way that it came from. Cool? All right. Did I hit everything in here? Let's see. Places where k is 0 are turning points. There the particle changes direction. To find the kinetic energy. Yeah, so I guess we should do that real quick. So all right, so EMEC is 5 joules. All right, so let's suppose my thing is at a position of x3. For this example, our mechanical energy is 5 joules. So if you're at x3, what would my potential and kinetic energies have to be?
3 joules and 2 joules.
Yeah, the potential energy is 3, right? And therefore my kinetic energy has to be the missing 2, right? Make sense? So I think that's kind of it for these potential energy curves. Let me see. We talked about stable and unstable equilibrium. I need to answer Dan's question about that point. Where it's half stable, half neutral. I don't know the answer to that. So did we hit everything? I think we did. Yeah, we looked at different points there. I think that's everything, right? Yeah. Cool. You guys don't have this, do you?
We do.
Oh, shoot. I didn't mean to give you that. All right. Everything that you've got here is garbage. That's left over from last year. Okay. Are we good with the potential energy curves? Sorry, that was not by any stretch my best